I don't think you can have.
He was dead. That's true.
Yeah, we got April.
All right, let's get started. Exam 1 is done. I was going to have it done on Friday. I was grading it on Friday, but I wasn't able to get it done. I had some students in another class that needed some help with one of their projects, and so I didn't get it done until this morning. But it's done. It's graded. Grade reports are distributed, and in the end, I think the class as a whole did fantastic. I'm tickled with everybody's performance. All the outstanding homework is graded, so I think now you have a really good, solid understanding of where you sit in the class. We only have 2 other exams left. The second exam is right before spring break, so we review. So it's the week before spring break. We review on Monday, celebrate on Wednesday, no class on Friday.
Very loud.
Yeah. Except for the capstone folks, they have class. They have a big day. So.
Oh, we have presentations.
Yes, you know. You got your capstone presentation. The alternative presentations that Friday.
Full suit. Full suit.
Yes.
I think that's serious.
Yes.
Wait, is that the actual one, or is it the actual presentation, or is that like a practice?
Well, you have 2 presentations. One's the alternatives, one's the final. I mean, you can think of it as your practice, but it's for a grade.
So we have to wear a suit for that one?
Oh, yes. Oh, yeah.
And they can't be
Yes.
Why?
It's called being professional.
But is there going to be other people here besides you?
Yes.
Okay.
And that will be immortalized on the recording forever.
Is Synergy coming?
They might, yeah. I might invite Zach to that. So. I mean, there's no pressure. It's not like it's the most important presentation you've ever made in your college career up until now. So.
Thanks.
You're quite welcome. No, it'll be all right. You'll be fine. You'll be fine. Okay. All right. So today we're going to begin our discussion of bolted connection design. And I want to tell you that bolted connection design for a bearing type connection versus a slip critical connection, the process is exactly the same with one slight addition. And that'll become clear here in a bit. We're going to spend next lecture, Wednesday, talking about slip critical connections. That'll be the only thing that we discuss. So with that, let me go ahead and just jump right into the land of bolted connections. So let's just recap the 2 fundamental strength limit states that we've been looking at so far, which is bolt shear capacity and bolt bearing capacity. When we get into slip critical connections, there'll be a third. There'll be bolt slip capacity. And it'll be a lookup just like bolt shear capacity is. So it won't be anything incredibly demanding. The theory is pretty easy to understand too, but we'll talk about that on Wednesday. But I think we would all agree that of the 2, the most labor intensive is the bolt bearing. I think really with bolt shear, the difficulty comes on the observation side of things at the very beginning. Because what you have to do is you have to look at the connection, recognize what group you're looking at, whether the threads are included or excluded, and if the problem doesn't say, you assume that they are included because that's the worst case scenario. You need to identify whether or not the bolts are in single shear or double shear, right? So that's really the challenge with bolt shear, is just being able to identify the parameters. The math is easy because it's just the capacity per bolt times the number of bolts. Remember with splices, you got to make sure that you're bookkeeping appropriately, but in the end, the math is pretty easy. For bolt bearing, that's the one that's the more labor intensive, but I would argue that it's also, I think, the easier one. Like, it's longer. I mean, there's more button crunching that you have to do, but it's not hard, I mean, you have your spacing, your edge distance. From those, compute your LCE and your LCI. From those, compute your 3 parameters and then your capacities. Add them up to get the nominal capacity. Don't forget to multiply by 0.75. So there's a lot of steps, but it's not hard. It's pretty straightforward. And then lastly, the layout requirements. We're going to use those layout requirements for the purposes of design today. But up until now, they've really just been a check. They've just been a means of checking whether or not the connection meets both bolt spacing requirements and edge distance requirements. Remember, if bolts get too close together, you can't tighten them, right? And the minimum edge distance requirement is there from a fabrication perspective as well. But if they get too far apart, then you run the risk of allowing water in between the plates, and that leads to corrosion, and corrosion's no good. So those are the reasons for your layout requirements. Again, meeting layout requirements doesn't mean that you meet bolt bearing capacity. Those are separate concerns. Now what we need to do is we need to talk about design. Okay, so design of a bolted connection is pretty easy. Okay, what we do is we determine the factored load. We determine the shear capacity of a single bolt, and then we divide to get the number of bolts. That's it. That's pretty much it. Sorry. Once we get that number of bolts, I have a statement here that says select a pattern accordingly. And let me talk about that a little bit. Okay? So when you compute the required number of bolts, it's not going to come out to be a nice, pretty number. It's going to come out to be like 14.62. Whatever. Okay? So 14.62 bolts. So round that up to 15 bolts. Okay? So let's say you have 15 bolts. Does that mean a line of 15 bolts? Or does it mean maybe a grid of 3 by 5? Or 5 by 3? Some sort of pattern that makes sense. Typically, you will want to collect that pattern as much as possible. So, for example, dependent upon your geometry, it's possible that, for example, let's say that our, for example, I see folks do this all the time. Let's say that we have the number of bolts required is 22.36 as you do that, okay? So the engineer in me says, well, do I want to round that up to 23 bolts? Well, I could, but 23 doesn't work out in a nice, pretty grid. So maybe I'll say 24. Because I could use 4 by 6 or some sort of neat pattern of bolts that make sense. Now, I could go with something like 23 bolts and maybe develop a staggered configuration. Maybe I could do that. But I'm trying, for the purposes of what we're doing here in this class, I want to keep it simple. So typically, I want to collect that into as grid-like a pattern as possible. Now, once I develop that pattern, I want to lay out the connection using the prescribed requirements. And so what that means for us is I have the number of bolts, and now I need to arrange them. And so when I'm in design mode, I want to use as little material as possible in order to meet the requirements. Because what I don't want, okay, just to make sure that we're on the same page, okay, so here's a tension member. Okay, so I would, I could have a tension member such that the connection, looks like this, and I have my bolts, arranged like that. Or I could have it like this, where I've spaced those bolts out about as far as possible. To me, this seems like a waste, right? I'm wasting material. I have a super long, gusset plate when I don't really need it, okay? So instead, I would prefer to use minimum bolt spacings and minimum edge distances when possible. When you have a problem in this class, you'll be told whether or not to use the minimum bolt spacing or the preferred bolt spacing, but we're always going to use the minimum edge distance for layout. Okay? Once you have a connection, right, so we know the number of bolts, we've laid them out, now we can check bolt bearing. Okay? And once we find whether or not it works or not, if it works, we're good. If not, we iterate if necessary. And what iteration means might be something like, let's say the bolt bearing check fails, maybe up your spacing by 1/4 of an inch or 1/2 an inch and try again, right? Okay, and I mention that because you are going to have to iterate on your next homework, so I'm just telling you that now. But I'll explain what that means when we actually get into the guts of the problem we're about to look at. Does this make sense? Okay. All right. Let's talk a little bit, though, about the really globally the potential options that you might have with iteration. So the whole point of checking the connection is to check it to ensure that it meets bolt bearing capacity. When you're in design mode, it will meet bolt shear capacity, and it will meet bolt slip capacity when we're looking at slip critical connection. There's not going to be any ambiguity of that. If you solve for the required number of bolts and you choose a number of bolts that's bigger than that, it's going to work. The bolt bearing check is the one that's going to be iffy. Okay. Now, if the connection fails in bolt bearing, you have a few options. What I think is easier is to increase the bolt spacing or the edge distance. And if you increase your bolt spacing by just like ½ an inch, that might work. That might be enough. Okay. That's usually the way to go if you just need a little bit more capacity. Just up your spacing a little bit, and that might be enough. Obviously, you can't increase your bolt spacing beyond the maximum, but that shouldn't be a problem in design mode. Now, another thing that you could do is you could stagger the bolts. Staggering the bolts would slightly increase the bolt bearing capacity because some of the bolts are going to have a larger edge distance. Okay, but that really is only going to slightly increase your bearing capacity. Staggering the connection, really the benefit of doing that is increasing your net area for net section fracture. For this, it'll help a little, but not a lot. Okay. Another thing that you could do is just increase the number of bolts. Like if you calculate your bolt shear, if you calculate the number of bolts and select that based off bolt shear, but then you go to the bolt bearing limit state and it is way low, then you might need to increase the number of bolts. But that's usually only needed if it's only done if you need much more capacity. There is a third option that I don't have listed here on the slide, but is something to consider. If you're at the point where your bolt bearing check is way off, like you don't have enough capacity, you could increase the thickness of the member, right? Because bolt bearing capacity is a function of the thickness of the plate. And so if your bolt bearing capacity is way low, you can increase the thickness. But I don't put that on here because keep in mind your tension member also has to meet gross section yielding, net section fracture, block shear rupture. And if you've got to increase the thickness in order to meet these limit states, chances are you're not meeting the other limit states, the gross section yielding, net section fracture, all those. And there's probably a bigger problem in store than just this. So that's why I don't list it. I mean, yeah, theoretically it would work, but again, you probably have bigger issues. And then finally, this is just a statement here in the slide about choosing a bolt pattern that makes sense. This is kind of what I wrote here on the board. So if you calculated you needed 10.46 bolts, I'd probably say use 12 because 11's a prime number, so it wouldn't be a nice, pretty grid. So, sound good? All right. I have mentioned this before, but I will say this. A lot of fabricators love to lay out, in the real world, they love to lay out their connections in 3-inch grids. So they like to use an edge distance of 3 inches and a bolt spacing of 3 inches. I'm going to require minimum LEs and minimum S's for our designs, but I put this out there because you will see this a lot in the real world. The reason for 3-inch grids is because a 3-inch bolt spacing and a 3-inch edge distance meets the requirements for 3/4 inches, 7/8 inches, and 1-inch diameter bolts, which are the 3 most common bolt diameters that we use in steel construction in the United States. So if you use a 3-inch grid, that drilling pattern tends to work for just about any bolt that you would use in any project. So if you have a large project that has a lot of multiple repeated connections, using regular increments like that can help the fabrication process, because even if it's a little inefficient on the design side, it can be really efficient on the fabrication side, because now you're just having to do the same drilling over and over and over again. Okay. I talked about this bullet last time. I talked about this bullet last time. I'm going to mention today how this would impact a design where instead of designing for a load, we design to develop the full capacity of the member. So in other words, we compute the load based on whatever the VPN is for gross section yielding or net section fracture. We actually use that as our design load. So the idea is that however many bolts we pick, we know it's good, because if we start failing the member, it's not going to be because of the connection, it's because gross section yielding and net section fracture was our governing limit state. But I'll show you where that would apply here on this example. So this is going to be our goal for today, to design and lay out this connection, or the bolted connection for this plate shown. So I have a 12 by 7-inch plate. I have 3/4 inch diameter Group B X bolts. So let me pull this up here. And we have A572 grade 50 plates. I've changed it up a little bit in terms of the parameters we've been using, because we haven't really been using a lot of A572 in our examples in class. So I said, what the heck, let's spice it up a bit. So we have a design load, or we have service loads of 115 kips of dead load and 160 kips of live load, and we're going to be laying out the connection. So all I know for the purposes of this design is I have a 12 by 7/8 inch plate lapped onto another, and I have no idea how I'm going to connect them. Okay. One thing that we can identify, though, just using some common sense, is that we have bolt shear and bolt bearing to check, but for the bolt bearing limit state, it's the same member, right? We have a 12 by 7 inch plate lapped onto a 12 by 7/8 inch plate. So we don't need to check 2 cases of bolt bearing like you might have had to do on the last homework assignment. Did that make sense, by the way, on that last homework assignment? How there were 2 cases, there was the W shape and the cover plates. And I think you found by observation you could ignore one of them, right? Because one of them had a lower FU and a lower thickness, so there's really no point in checking the other one. So you can check both if you want. I think in the solution, I checked both just to show you that you can see one isn't going to govern, but I'll do the math to show you. So, make sense?
So we could have just wrote that on. I mean, it was obvious, but
yeah, I was totally fine with that. I'm serious. I have no problem with that. I have no problem with you using that engineering judgment. Okay, let's get into it, okay? So our first step is going to be to compute the factored load, right? So, where'd my pen go? There it is. It's all tangled up here. Okay? And I think by now, this should be pretty easy, right? 1.2 dead plus 1.6 live. I don't think that's terribly confusing, right? So this is 1.2 times 115 kips plus 1.6 times 160 kips. And when we chug that out, what do we get?
394.
394. Do I have a second?
Yep.
All right. Okay. Now I want to take a little bit of a deviation over here off to the side. So if we were designing to develop the full capacity, okay, what we would do is we would say, okay, so in that realm, if I said to design to develop the full capacity, I would not be giving you a dead load or a live load because you wouldn't need it, right? The whole point is you don't need a load to develop the full capacity because you're using the member to generate that load. So what we would do is we would say our design load is the minimum of 0.90 Fy Ag or 0.75 Fu ANU, right? And we could throw block shear in there if we wanted to. Typically, like as an engineer, I probably would not in design mode, because block shear is really a function of the connections configuration. If I'm in design mode, I really don't know what that is. And I'm sure some of you are thinking, well, wait a minute. Y'all's net area and U are a function of the sections configuration, and that's true, okay? But what I would do for this is I would say assume that. And if you remember, we did this. This is what we did in tension member design. Remember how we assumed that the effective net area was about 75% of the gross area? So when we were computing that AG design, it was the minimum, that denominator was the minimum of 0.9 FY or 0.75 squared FU. Remember, one of those 0.75s was a resistance factor, and the other came from the fact that we were assuming that was about 75% of the gross area. So if I didn't give you a load, I would probably say do this. So I'm just throwing that out there. Does that make sense? Okay. Now, the second step is going to be determine phi RN for a single bolt. So in order to do that, we're going to need to recognize a couple things. This is group BX. We were told that. Is it in single shear or double shear? Single shear. And we are told that the bolt diameter is 3/4 of an inch, okay? Which, if you didn't know the bolt diameter, or you really didn't know anything about the bolts that you were going to use, I think in my mind, I tend to go with Group A, threads included, 3/4 inch diameter bolt. Like those are just your bread and butter, the most common bolts you're going to find. Like if in this problem, we know that we're using those bolts. We just need to figure out how many of them and in what pattern. But if you don't know, that's probably what I would go with, just for their sheer volume of use, in the United States. Okay. So what is the capacity of this bolt in shear?
27.8.
27.8. Do I have a second on that?
Yeah.
Okay, so this is 27.8 kips per bolt. And this is table 7-1. Now, just so you're aware, we are just looking up the shear capacity in step 2. When we look at slip critical connections, we're going to look up the shear capacity and the slip capacity and take the smaller one. Past that, everything else is the same. Nothing else changes. So next thing, number 3. Determine the required number of bolts. So I have 394 kips on the connection. I have 27.8 kips per bolt. So pretty easy. So this is 394 kips. So 394 kips per bolt, and if each bolt can hold up 27.8, how many bolts do we need to use? Well, what does this formula yield?
14.17.
So, how many bolts do you think we should try out for this connection? 15, right? So we'll say try 15 bolts. So we'll break that. So, now we got to lay them out, okay? We need to look at bolt spacing and bolt edge distance requirements. Okay. So, now we need to lay out the connection. So let's lay this connection out. Okay. So what is LE min going to be?
1.
1 inch. And where'd you get that?
J 3.34.
There you go. This is table. Table J 3.4, right? Okay. Now what about S min? We're going to use S min for this problem. S min is what? That one's a computed value, right? It's a fraction times the bolt diameter. What's that fraction? 8/3. Okay. So what is that? That's 2 inches?
Yeah.
Okay. All right. Now we go back to 3rd grade and we say 15. If we factor that, that goes 3 times 5, right? But it can also go 5 times 3. So that begs a question. Okay? We have 2 ways of laying out this connection. Option 1, that's option 1, right? Okay? But, now hold on, here's option 2. Let me do this another way. Option 1, option 2. I'm drawing it a little bigger because I'm going to have more holes here. But the dimension's the same. All right. Now, what would be the advantage of option 2? Well, option 2 would require less plate for it to connect to, right? Option 2 only goes out here. Option 1 goes all the way out here. We would need more of that plate lapped onto it, right? That's going to cost money, right? So I am wanting to make this connection as compact as possible. But is this going to work, right? Well, let me ask you this. If I space everything out evenly, okay, remind me, what is this dimension right here? What is that dimension? 12 inches. So if everything's spaced evenly, what's that dimension right there? How many gaps? 1, 2, 3, 4, 5, 6. If everything's even, what is that dimension? 2 inches. Is that going to meet our requirements? Yeah, it is, right? So I can space these out both 2 inches this way and 2 inches this way, and that meets the requirement, and I still have enough room. All right, I can make this dimension here 1 inch, the minimum edge distance requirement, and then this dimension here, make that 2 inches. Use the minimum spacing all around, collect those bolts as tightly as possible, and here's my trial layout. So I'm actually going to draw my trial layout again, make it a little bigger to make sure that it's completely clear what my trial connection layout is going to be. Again, forgive my horrible scale here. This is 1 inch, 2 inches, 2 inches. This dimension here is 2 inches typical. This is 12 inches. This, and I'm yanking on it, you know, like that. This that's my trial connection layout right there. So, the point I'm making is if I check bolt bearing and bolt bearing works, that's the answer. This is the answer, not x equals 3, right? This is the actual answer, this connection design. Does that make sense? But we don't know whether or not this is going to work because we have to check bolt bearing, right? And remind me, what was our factored load on this problem? What was PU? So we need to ensure that we have enough bearing capacity, bolt bearing capacity, such that the PRN is greater than that. Now, before we move on, I just want to make sure that everybody's paying attention. Ahead of myself. How many edge bolts are in this connection? How many interior bolts are in this connection? 5 and 10. These are my edge bolts. These are my interior. Okay. All right. Does that make sense? If that makes sense, the rest of this is not hard. It's just a bunch of calculations. Like it's rows, pretty step by step. Everybody with me? Second? All right, so now let's check bolt bearing. All right, check bolt bearing. All right, so in order to check bolt bearing, we need some values. So we have S is 2 inches. We have our edge distance is 1 inch, right? And one thing I want to make sure I'm clear on, these edge distance requirements and bolt spacing requirements, remember, they are independent of what load you're putting on. They're for different reasons. So you have to make your bolt spacing limit states both this way and this way. Your edge distance requirements both this way and that way, okay? So make sure that you're adhering to both in every direction, right? So we have a plate thickness we're going to need. What was the thickness of the plate for this problem? Was it 7/8? 7/8. We're going to need the bolt diameter, which is 3/4 of an inch. So therefore, the hole diameter is what? 13/16. And finally, we're going to need an FU value. What is FU for A572 grade 50 plate?
65.
65 KSI. And this is table 2-5. Okay. So the rest of this is pretty rote, right? So what do we start off with? We start off with LCE and LCI. LCE is LE minus half of the hole diameter, which, if you're okay with this, I'm just going to go ahead and tell you, ends up being 0.594 inches. Is that okay? Right, and then the LCI is S minus DH, which that ends up being 1.188. So that's sort of the first step of calculations that you need to do. then the next step that you need to do is 1.2 LCE TFU, which ends up being 40.52 kips. Then 1.2 LCI TFU, which ends up being 81.05. And then 2.4 dBTFU, which that one ends up being 102.38. Then the next thing that we do is, oh, I need to make that a little bigger. So then we say that RNE is the minimum of the top one and the bottom one, which we can observe and see is 40.52. And then RNI is the minimum of the lower two. Which is, obviously the tear up one as well. All right. Then now these are the capacities of each individual bolt, but we need the capacity of the connection. The capacity of the connection is 5 edge bolts plus 10 interior bolts, right? So when we chug this out, we get, it's a big number. It's 1013.1. And then, what did I forget? Feet. Got to multiply by 0.75, our resistance factor. And so when you chug that out, you get like 759.8. Is that good? How can we tell whether or not this connection has adequate volt bearing capacity? What are we comparing against?
Less than 394.
Needs to be, no, greater. Greater. This is the capacity, this is our load, so we need to ensure that we have enough volt bearing capacity to withstand this load. And we do, and then some, right? We certainly have enough. So remember, PU So I'm basically saying that that's the answer, but when I say that's the answer, I'm saying that that layout works. That's our design. And that is bolted connection design in a nutshell. Okay? So I want to stop for a second and see if anybody has any questions about this so far. Because I want to bring up a couple things, and I kind of want to introduce the next lecture so that we don't get time crunched during our lecture on Wednesday. But you tell me, was this confusing, simple? Everybody good? All right, So I want to ask you a question, okay? We got, what was it? FERN 759.8 kips. My question for you is, what if we got 359.8 kips? What would that mean? I'm asking you. It's not good, right? Because this is our load, this is our capacity, and when comparing the two, that would not have enough capacity, right? So I want you to go through that thought process in your head, okay? So we solved for the required number of bolts, we laid them out, we checked bolt bearing, bearing's not good. So how do we fix it? Well, the problem is in this step, okay? And this step was a function of all these different parameters right here, okay? These were the critical parameters. So what I propose is, if for some reason your connection doesn't have adequate capacity, the problem is in that box right there. And a lot of these, you're not going to change at this stage of the connection layout, especially if the capacity is just a little bit lower. My advice would be to change one of these two, preferably the spacing, okay? So I want to pull up the homework and kind of make a point about what's going on this this next homework, or on this next problem. So this is going to be the problem that you have to do. All right. So I mentioned a couple of things. So we have a C10 by 15.3. You're going to design this using a dead lead of 30 kips, a live lead of 50 kips. I want a sketch of your design at the end when it's all said and done. Assume that you're using 3/4 inch Group A bolts. Okay, one of the things I told you to assume at the beginning is that there's 2 lines of bolts, right? So there's 2 lines, right? So it's 2, 4, 6, 8, 10, 12. So whatever, so that makes the layout easy, right? Because whatever you calculate, round up to the next even number, and that's how many bolts that you use, right? Because you're going to use 2 lines of bolts, okay? I want you to use S-min and LE-min to lay out your connection. And for bolt bearing, you don't need to check the gusset plate, just check the channel. So that makes that part easier. But you might find that connection fails in bolt bearing after step 5, and if so, try increasing your bolt spacing by 1/2 inch increments. Okay? I don't know what else I could say. You're giving me that look like.
I see what the iterations are for now that you speak of.
Yes, these are the iterations I was talking about. It's not going to be that bad, but you will, doing this correctly, you will most likely have to iterate.
He said we'd have to iterate at least 3-4 times.
I did not say that. You're trying to get me in trouble, Mr. Lingenfelder. I'll remember that.
That's just what I heard.
I don't know who told you that. I didn't. All right. We got a few minutes. I just want to kind of introduce the concept of a slip critical connection. Just to give you all kind of an idea of how a slip critical connection works. So, in the process of a design for a bolted connection, this is the process we just followed, right? Whenever you're doing a slip critical connection, the only thing that changes is step 2. And really the only thing that changes is that instead of just the shear capacity, we're going to take the minimum of either the shear and the slip capacities, okay? So that means we have to talk about slip critical connections. I'm just going to introduce the idea. I'm not really going to get too far into it today because we don't really have time to get into the details. But if you remember when we talked about a bolt assembly, we said that there were really 3 mechanisms to resist load. There was the shear force inside the bolt. So in other words, if we exceed that, we shear the bolt in half. There's the bearing on the plate, so the bolt's actually bearing on the plate, and so if we exceed that resistance, then the plate will either mash up or it'll tear out. But then the third was friction, right? Friction can actually develop between the 2 plate surfaces as the bolt forces those 2 plates into contact. Slip critical connections rely on that friction to resist the load. They're very common in bridge applications, and they can also be used on joints where you have oversized holes or slotted holes, earthquake scenarios, or where slip critical connections get detailed a lot. So that's really where we see slip critical connections utilized. Now, to install a slip critical bolt, first we have to get the bolts snug tight. And that's actually a good question. What does it mean by snug tight? That's actually defined in the specification. Snug tight is the tightness that you get either with a few hits of an impact wrench or the full effort of an iron worker using an ordinary spud wrench. Basically the idea with snug tight is that snug tight has to get the contact surfaces firmly bearing with one another. Once that happens, you have to use a prescribed method to achieve the required torque. And that's going to be a lot of what we talk about in class on Wednesday. And so I think I had mentioned, for those of you that had been on a DOH site where they had installed a steel girder bridge, I think you had said you had done that. Did you see those? So that's what these were, right? So this is one of the prescribed methods. I want to give this its proper time in the sun, so we'll do that on Wednesday. But there are a series of methods that we can use to develop slip critical capacity. But the short answer from a theory perspective is that if you want to know what the capacity of a single bolt is under slip, it's basically this with some correction factors. And this is a formula that everybody here should recognize, right? Because this is basic physics, right? A coefficient of static friction times the normal force equals the amount of friction developed between those two surfaces, right? I remember teaching some of y'all that in Engineering 213. I think I did. All we do is we use this and we just correct it for a few different things, but that's kind of where we're headed. I don't have time to talk about that today, so we'll talk about that on Wednesday. All I'm going to do is pull up the code again in case anybody missed it, and we will talk about this on Wednesday.